Hi guys, it's Daniel here, and today we are going to do another coordinate geometry problem. And this problem is 2002 AIME 2 problem number 15. In other words, the hardest problem of the AIME 15. So it might take a little bit of time, so I apologize in advance for that. So without further ado, let's begin. First we have that circle C1 and C2. They intersect at 2 points, one of which is 9, 6 here, and the product of the radii is 68. The x-axis and the line y equals mx are all both tangent to this, so here they are, y equals mx. And we want to find m. So with all this information, it was kind of confusing on how we should put them together. I mean, like, we have two circles, they intersect 9, 6, and they're both tangent at y equals mx and the x-axis. And the strangest thing is that we have to use the product of the radii is 68. I mean, like, I was pretty confused on how to do this. So first, I focused on things that I could figure out easier. For example, what types of circles can go through 9, 6 in the x-axis? That's the first thing I asked myself. And so in order to find this out, I first connected some important points with some other important points, with the centers of C1 and C2 with the 9, 6 and the tangency points. And we can see that since they are radii, these are equal, these are equal. Now this setup reminded me of something. If we have a point and a line, and we have these points which are equidistant from the point and the line, they form a parabola here. And this is the exact same setup as here, because the center of C1 and the center of C2 are both equidistant from 9, 6 and the x-axis. So therefore, they lie on a parabola right here. In fact, that's a bad parabola. Right here. There we go. In fact, this parabola classifies all possible circles that go through 9, 6 and are tangent to the x-axis. Because this parabola has that no matter which point you pick as the center of the circle, the distance between this point and 9, 6 and this point and the x-axis are the same. So therefore, all possible circles that go through 9, 6 and are tangent to the x-axis have centers on this parabola. Now, just knowing this parabola doesn't really tell us much. So, because how are we supposed to relate this parabola to y equals mx? There really isn't any clear way. If we connect the tangent lines here, then how are we supposed to find y equals mx with the parabola? It seems completely useless. But then, this is where the second insight comes in. What if instead of using y equals mx, we use this line? Let's call it y equals kx. Now, before using this line, some of you might be questioning whether this line that goes through the centers of C1 and C2 actually goes through the origin. And this is easily explained because C1 is a homothency of C2, or the other way around, with center at the origin, which basically means that if you take the origin as the center and blow up C1, it will turn into C2. So because C1 and C2 are homothencies, then it tells us that if we connect C1 and C2, it also goes to the center of homothency, which is the origin. So that explains why the line through C1 and C2 also goes through the origin. Now, how does this line help? Well, there are two things that helps. First thing is that if we can find the equation of this line, we can find the equation of y equals mx, because this line is the angle bisector of y equals mx in the x-axis. So with some simple trigonometry, we can find y equals mx. The second thing is, notice the intersection of y equals kx and the parabola. is the centers. So if we can find the solutions to the intersection of y equals kx and the parabola, then we can find the centers. And with the centers, we can find k, and with k, we can find m. So the only thing that's missing now is to find the equation of the parabola. Fortunately, this isn't too hard, because two things. First thing, we can easily find the vertex. The vertex is simply the midpoint of the shortest distance from the from the focus to the directrix, so which is focus here and the directrix here. And since the height is 6 because of 9, 6, this length is 3 and this length is also 3. So that means the coordinate of the the vertex is 9, 3. And this is 9, 6. Now we can plug in this to form almost the equation by vertex form. The only thing that's missing now is this a right here. We don't know how fast the parabola opens up, like how wide it is, but fortunately we can also find that out, because we know that 1 over the absolute value of 4a is equal to the distance from the directrix to the vertex, or from the focus of vertex, same thing, which is equal to 3. And this tells us that a equals 1 over 12. So therefore, the equation of this parabola is y equals 1 over 12 x minus 9 squared plus 3. Now we know the equation of the parabola, y equals 1/2 x minus 9 squared plus 3, and the equation of the line, y equals kx. We can find the solutions now by plugging in kx equals 1/2 x minus 9 squared plus 3. Now, once we expand x minus 9 squared and then rearrange some stuff, we get that this is equivalent to x squared minus 12k plus 18 x plus 117 equals 0. And now we know the equation, which gives us the roots as the x-coordinates of the centers of circles C1 and C2. So with this, let's list out a few things that we know in order to find an organized approach to finding k. So first thing, if we call the roots of this quadratic equation x1 and x2, which correspond to these 2 points, the coordinates of x1 and x2, then first of all, by Vieta's, we know that x1, x2 equals 117, and x1 plus x2 equals 12k plus 18. Second thing we know from using the line y equals kx, let's first suppose that this length is r1 and this length is r2, is that r1 equals kx1 and r2 equals kx2, because that's what you get when you plug in these coordinates in the y equals kx line. Finally, there's one more thing that we have not used yet, and this is our strange property that was given to us. The product of the radii is 68. Fortunately, with this, we can easily represent this because r1 times r2 equals 68. Now we have this information here, and let's see if we can find k. Well, first off, let's plug in r1 equals kx1 and r2 equals kx2 in, and this gets rid of the r1 and r2. So these two equations gives k squared x1 x2 equals 68. But wait a second, x1 x2 equals 117 because that's here. So therefore, k squared equals 68 over 117, which means that k equals square root of 68 over 117. And now we know that the equation of this line is now y equals square root of 68 over 117 of x. Now we're almost done. Now that we know that the equation of y equals kx, we can find the y equals mx through some basic trigonometry. First off, let's call this angle theta over 2. So this angle is theta. Now we know that tangent of theta over 2 is equal to k, which is equal to square root of 68 over 117. And tangent of theta is equal to m, because tangent is defined as the rise over 1 run, which is also the definition of slope. Now, by using the double angle identity for tan, which is tangent of 2 theta equals 2 tangent theta over 1 minus tangent squared theta, we can find tangent theta in terms of tangent theta over 2. This is just tangent theta equals 2 tangent theta over 2 over 1 minus tangent squared theta over 2. And since we know that tangent theta over 2 equals square root of 68 over 117, this is just equal to 2 square root of 68 over 117 over 1 minus 68 over 117. This simplifies to 12 square root of 221 over 49, which is equal to m. But wait, look at what we were trying to find. M is written in the form a squared to b over c, and this is exactly the form that we have for m right here. So that means we're basically done. All we have to do is do 12 plus 221 plus 49. This is equal to 282, and we're done. Hi guys, it's Daniel here, and today we are going to define what a weird number is. These types of numbers is related to abundance